Hello, my name is Jesse Baker and I'm an applications engineer supporting position sensing products. In this video, I will discuss how to use the TI Magnetic Sense Simulator, TIMS, to simulate hinge type motion using magnetic sensors. Hinge motion is commonly used in laptop lid closures and other lid and door detection applications. In TIMS, the hinge function involves a magnet that pivots around the x-axis. When this type of motion is selected in TIMS, there are a few key input fields used to define the travel of the magnet. These can be found by clicking to expand the magnet motion dropdown. The first is the origin position. This will define the initial starting position of the center of the magnet. Using the x-axis, y-axis, and z-axis inputs, it is possible to place the magnet anywhere in 3D space near the sensor. Normal lid close simulations have a displacement in the y direction for both the magnet and sensor, with each separated by some distance in the z direction. The second row within the origin position section will define the orientation of the magnet. Since the magnet is polarized in the z direction by default, it may be necessary to rotate about the x or y axis to match the desired alignment to the sensor. All rotations are carried out in XYZ order. Keep in mind that the magnet will always pivot around the global x-axis in the 3D space when using the hinge function. The last field in the magnet motion category will define the arc length in degrees that the magnet will rotate about the x-axis. The last relevant configuration setting is found after selecting Sim Settings at the top of the input menu. The angular step size field allows the user to define the angular step size for the simulation in degrees. The tool will create as many evenly sized steps that can be divided from the total arc traveled by the magnet. In this design example, a neodymium type N52 bar magnet with dimensions of 4 mm by 8 mm by 1 mm is used. The sensor and magnet are both offset 20 mm in the y direction away from the hinge axis. The sensor is offset 3.6 mm in the z direction, while the middle of the magnet is offset 10.6 mm in the z direction. Finally, note that the sensor is 1 mm offset from the magnet in the x direction. To demonstrate, I'll walk through how to configure this example simulation setup using the tool. In this case, I will select hinge for the function type and will use a bar magnet for this example. For the sensor, I will pick a Hall effect switch that we can use to detect the changing Z component of the magnetic field. For this, I have chosen DRV5032. With all of these inputs selected, we are ready to start configuring the simulation. I will select the magnet material as a neodymium type N52 magnet and will set the geometry to 4 mm by 8 mm by 1 mm. I can configure for the lid closure detection application by setting the start position to 20 mm in Y and 10.6 mm in Z. I will set the arc length for the path of rotation about the x-axis as 120 degrees. I will update the sensor specification tab to select the DRV5032 DU DMR variant of the DRV5032. I will also set the BOP to BOP max and BRP to BRP min. I will use the sensor position tab to offset the sensor 1 mm in the x-axis and set a Y position of 20 mm and Z position of 3.6 mm. Finally, I will leave the angular step size as 1 degree. We see that when the simulation completes that we can observe the travel of the magnet about the x-axis by clicking play, with the complete magnetic field information plotted on the right. We can see that the field for this type of motion is mainly in the z direction under this alignment, and that the magnetic flux density will decrease as the magnet rotates away from the sensor. If we disable the magnitude, Bx, and By fields in the plot, we can more clearly see the field in the z direction. This type of motion is commonly used for lid open and close detection functions, and is often implemented using a Hall effect switch like the DRV5032 DU DMR. This device has a maximum operating threshold of 3.9 millitesla and a minimum release threshold of 0.9 millitesla. If we compare these thresholds to our plot, we would expect to see the device operate and release within this window. Note that it is wise to run these simulations using the maximum operating threshold and minimum release threshold for the sensor to ensure these corner cases are accounted for. These settings can be configured under the Sensor Specifications tab in the TIMS simulation configuration. Comparing to the output plot generated in TIMS, we can see that the expected transitions are displayed for both forward and reverse travel. In this case, forward motion represents the magnet moving away from the sensor and releasing at around 35 degrees, and reverse motion represents the magnet moving toward the sensor and operating around 13 degrees. That shows how to simulate hinge motion in TI Magnetic Sense Simulator. To learn more about TIMS and this type of motion, please see the relevant collateral linked here. To get started on your hinge motion simulation, please visit www.ti.com/TIMS.